Kimi K3 just became downloadable, all 1.56 terabytes of it, and your gaming PC still cannot run it. This is the official Hugging Face repository. The full Kimi K3 weights are public, not a demo, not an API connector, and not a smaller distilled edition. Open the file list and the scale becomes real. The repository is split across 96 numbered weight shards, with most individual files landing near 17 gigabytes. Together, those files reach 1.56 terabytes before you have served a single token. And the model is not one huge mystery blob. It arrives as 96 separate weight files that deployment software has to coordinate. What actually dropped is the model code, configuration, tokenizer, license, and the numerical weights that determine Kimi K3's behavior. That makes Kimi K3 open weight. Researchers can inspect and modify it, and infrastructure companies can host it privately. But public weights do not automatically mean laptop-sized local AI. The reason is architecture. Kimi K3 contains 2.8 trillion parameters in total, while about 104 billion are active for each token. The 2.8 trillion figure explains the enormous download. Every stored expert still has to exist somewhere. The 104 billion active figure explains why generation is more efficient than firing all 2.8 trillion parameters on every step. Kimi K3 does this with a mixture of expert system. 896 experts exist, but the router selects only 16 for each token. All 896 experts remain in the downloaded model, which is why sparse activation does not shrink the repository itself. Only 16 experts per token receive that token, which cuts active compute without turning a trillion parameter download into a consumer model. Think of the router as a dispatcher. First, your next token enters the network and is scored against the available experts. Second, the router chooses the small specialist subset that appears most useful for that token. Then 16 experts process the token and their outputs are combined before the model moves to the next one. Kimi K3 also advertises a 1 million token context window, giving long coding sessions much more room for repositories, requirements, logs, and previous tool results. That context is useful working space, not perfect memory. Kimi K3 can still miss details, follow a bad plan, or receive a tool history that your coding client mangled. Now put that model beside the machine most people mean when they say local AI, one strong gaming PC with one consumer graphics card. The mismatch is not subtle. A gaming PC may offer tens of gigabytes of fast graphics memory. Full Kimi K3 begins with more than 1,500 gigabytes of weight files. A normal gaming PC can store pieces of the download, but it cannot hold and serve the full Kimi K3 model at useful speed. Moonshot's own deployment guidance points in the opposite direction, a supernode with dozens of linked accelerators, high-speed interconnects, and data center cooling. The official recommendation is 64 or more accelerators for a supernode deployment. That 64-plus accelerator supernode is the machine class Moonshot discusses for full self-hosting, not a tower underneath your desk. Disk capacity is only the first gate. Useful serving also needs distributed fast memory, accelerator bandwidth, networking, and enough cooling to keep the cluster alive. Even the software stack tells the same story. Full self-hosting means sharding Kimi K3 across an inference engine such as SGLang or vLLM and coordinating the entire cluster. So yes, the full model can run on infrastructure you control, but for ordinary users, calling that local AI hides the only part that matters, the hardware bill. Hardware is the catch, but capability is why anyone would build that cluster. Moonshot's own demos move far beyond a chatbot answering one prompt. The published examples include long horizon coding, a compiler built from scratch, vision-guided game and interface development, and a 48-hour autonomous chip design run. The visual coding loop begins normally. Kimi K3 writes the code and launches the application. Instead of trusting the source code alone, Kimi K3 renders the page or game into something it can actually see. It then inspects the screenshot for visual mistakes that a text-only coding loop might never notice. Finally, it patches the project and repeats the loop. That is much closer to real software work than generating a landing page once and declaring victory. Moonshot also shows Kimi K3 creating MiniTriton, a compiler project built through a long sequence of terminal work, tests, and self-corrections. The most extreme example is a chip design task that Moonshot says Kimi K3 continued for 48 hours. That run reportedly produced a simulator operating at 8,700 tokens per second. Impressive, but still a vendor demonstration, not an independent lab result. The benchmarks deserve the same discipline. On Terminal Bench 2.1, Kimi K3 scores 88.3, Claude Fable 5 scores 88.0, and GPT 5.6 Sol scores 88.8. Kimi K3 at 88.3 is effectively in the same terminal task band as both closed systems. GPT 5.6. Sol still leads this specific table at 88.8. Close is meaningful, pretending Kimi wins would not be. On BrowseComp, Kimi K3 reaches 91.2, ahead of Claude Fable 5 at 88 and GPT 5.6 Sol at 90.4. Here, Kimi K3 is the published winner, but the margin over GPT 5.6 Sol is less than 1 point. On OSWorld Verified, Claude Fable 5 scores 85.0, Kimi K3 scores 84.8, and GPT 5.6 Sol scores 83. Claude Fable 5 takes that 1 by 2/10 over Kimi K3. Again, this looks like the same competitive tier, not one model crushing the field. The wider table is mixed. Kimi K3 leads program, bench and BrowseComp here stays close on OSWorld and trails both closed models on DeepSWE. Before turning that table into a victory speech, note the first caveat. These are Moonshot published results, not a neutral benchmark run we controlled. Second, every Kimi K3 score shown here uses its maximum reasoning setting, which can change latency and cost. Third, the compared models use different coding and agent harnesses. That makes the numbers informative, but not a perfectly controlled head-to-head experiment. The honest benchmark read is therefore narrower. Kimi K3 belongs in the same conversation as the strongest closed coding agents. Kimi K3 wins some published tasks, loses others, and makes open weights the differentiator, not a claim of universal superiority. The closed frontier models still win parts of the table and may offer a smoother product experience. Open weights do not erase that advantage overnight. The license is permissive for most developers. You can use, modify, distribute, and commercially deploy the weights, subject to Moonshot's stated conditions. Large model-as-a-service operators above $20 million in revenue across a consecutive 12-month period need a separate agreement, and very large products may face a Kimi K3 display requirement. There is also an integration detail agents cannot ignore. First, Kimi K3 returns reasoning content and tool calls as part of its assistant message. Your coding client must preserve that complete message and send it back on the next turn. Strip the reasoning history, and you remove part of the state Kimi K3 expects. For most viewers, there are 3 realistic ways to use Kimi K3 today: Moonshot's own products, a hosted provider, or full self-hosting. Kimi products are the simple route. You get the model's coding and agent features without owning the cluster. A hosted provider can expose the open weights through an API while competing on price, speed, privacy, and deployment region. Full self-hosting gives maximum control, but it is the data center option, not tonight's LM Studio download. That is the real release. Kimi K3 did not suddenly become a laptop model. It became a public infrastructure model that anyone with enough hardware can inspect, adapt, and serve. The weights are finally public. Now the interesting race is who can compress, serve, and independently test Kimi K3 without hiding the catch.